proof of Poincare conjecture. In mathematics, the Poincare conjecture is a theory about the characterization of the 3D sphere, which is the hypersphere that bounds the unit ball in 4-dimensional space. The conjecture states everything politically connected closed 3D manifold is homomorphic to the 3D sphere. An equivalent form of the conjecture involves a coarser form of equivalence than homomorphism called homotopy equivalence. If a 3D manifold is homotopy equivalent to the 3D sphere, then it is necessarily homeomorphic to it. Proof. The point is to discern whether an object is torus, a sphere, using entropy and manifold in metric space. Rho z is the vacuum entropy of an object, n is a dimension of an object which is proportional to h, and h is the number of holes in that. And max entropy is entropy which is proportional to surface area of the object, so surface area of an object is proportional to number of holes. And when surface areas of two objects are same, there exists one-to-one correspondence function between them. And it is obvious there exists continuous function between metric spaces. So within this relation of entropy, number of holes, and surface area, it is obvious. 3D manifold with no hole is homeomorphic with 3D sphere. Then let's prove above relation. Holographic principle. If we do treat black hole as an ordinary quantum mechanical object, an important implication would be the holographic principle. Consider an isolated system mass, energy, and entropy as zero in an asymptotic flat spacetime. Let A be the area the smallest sphere hat encompasses the system, and MA to be the mass of a black hole with the same horizon area. We must have E should be smaller than MA, otherwise the system would be already a black hole. Now, add MA minus E energy to the system. You shall obtain a black hole with mass MA since whereas prime is the entropy of added energy, we conclude that the maximum entropy inside the region bounded by area A is this. Recall the definition of entropy in quantum statistical physics is this, where rho is the density matrix for the state of system. For a system with n-dimensional Hilbert space, hence the effective dimension of the Hilbert space for a system inside the region of area is bounded by this. Remarks for a system of n space, the Hilbert space dimension n is e to the n. The dimension of h for a single harmonic oscillator is infinite, but for a quantum system is finite number of degrees of freedom. The dimension of h below some finite energy scale is always finite. That's why we have effective in the above description. In typical physical systems, number of degrees of freedom is log n. Just we can write this. The bound is violated in non-gravitational systems whose number of degrees of freedom is proportional to the volume rather than area of the system. For lattice of spins with lattice spacing, a total number of spin is this. For large enough R, also n is this. We have max entropy is this for large enough volume. In other words, quantum gravity leads to a huge reduction of degree freedom. Holographic principle. In quantum gravity, a regime of boundary area of A can be fully described by no more than these degrees of freedom. Degree of freedom per Planck area. Black hole brings quantum gravity to a microscopic level. Large and expansion of gauge theories. We now look at clues to holographic duality from field theory side. Consider quantum dynamics, which can be described as S3 gauge theory with fundamental quarks. The Lagrangian leads this, where the mu is this, are 3x3 Hamilton matrices and can be expressed as this with this. In such a theory, coupling becomes strong in IR. There is no small parameter to expand. It is still an open problem to derive IR properties of quantum dynamics from the first principle. Hoofed in 1974 suggested that take number of color n equals 3 as a parameter. Promote a mu to n by m Hamiltonian matrices and consider n to infinite limit and do a 1 per n expansion. It is an ingenious idea. Unfortunately, QCD still cannot be solved to leading order in the larger limit. Surprisingly, there is a correspondence between the large and gauge theory and the string theory. The key is the field of matrices. As an illustration, we will consider scalar theory. This, where G is the Cooling constant, is n by n Hamilton matrix. In terms of component, Lagrangian is this. Lagrangian is invariant under UN global symmetry, where U is any constant UN matrices. Remarks, it is a theory of n-squared scalar fields. One can also consider other types of matrices, and by a real symmetric matrix, the corresponding symmetry will be SON. One could also introduce gauge fields to make the UN symmetry local. Here, we list the Feynman rules for this theory: the propagator, the fermion vertex. So, here we can adapt the double line notation. Vacuum energy. We consider vacuum bubbles, diagrams with no external legs. The lowest order diagrams will be this. In the case of diagram 1, each contracted index line gives n. So the total contribution will be of the order this. In the case of diagram 2, there is only one contracted line. The total contribution will be of the order ng scale. The difference comes from the fact that the matrices do not commute. In the first case, the diagram can be drawn on a plane without crossing lines. We call it a planar diagram, while in the second case, the diagram cannot be drawn on a plane without crossing lines. We call it a non-planar diagram. If we consider next order in the perturbation theory, the first diagram gives the order of n to the fourth g to the 4. The second diagram gives the order of n squared g to the 4. We can further consider higher order diagrams, but how can you obtain general n counting, and how to classify the non-planar diagrams? To answer the above questions, we make two observations. Diagrams 2 and 4 can be drawn on a truss without crossing lines. The power of n for each diagram is equal to the number of faces in the diagram after we straighten it out. In fact, orient of two-dimensional surface is classified topologically by an integral H, the genus. The genus is equal to the number of holes that the surface has, figure 1. Topological invariant of the manifold is the overless character. Here we make some claims. For any non-planar diagram, there exists an integral H such that the diagram can be straightened out on a genus H surface, but not on a surface with a smaller genus. For any non-planar diagram, the power of n that comes from contracting propagators is given by the number of faces on such a genus H surface, the number of disconnected regions separated by the diagram. Both claims are self-evident after bit practices. In general, a vacuum diagram has the following dependence on g² and n. Where E is the number of propagators, V is the number of vertices, F is the number of faces. This does not give a sensible n to the infinite limit or 1 per n expansion, since there is no upper limit on f. However, Hooft suggests that we can take the limit into infinity and g square go to 0, but keep lambda is g square and fixed. Then this is true. Where L is the number of loops, the relation chi is f plus v minus e is guaranteed by the following theorem. Theorem: given a surface composed of polygons with f faces, e edges, and v vertices, the only case to satisfy is since each Feynman diagram can be considered as a partition of the surface separating it into polygons, then the above theorem works for our counting in N. Just in this limit to the leading order in N is the planar diagrams. This because log z evaluates the sum of all vacuum diagrams, we can conclude including higher order 1 per n square corrections. The first term comes from the planar diagram, second term from the genus 1 diagrams. There is a heuristic way to understand log z. Since z is this, and we can rewrite the Lagrangian as this. The trace also gives a factor of n shows Lagrangian O(n) square. We have log z's O(n) square. Clearly, our discussion only depends on the matrix nature of the field. So for any Lagrangian matrix valued field of the form this, we would have this. To summarize, in the Hooft limit, 1 per n expansion is the same as the topological expansion in terms of topology of Feynman diagrams. General observables. Now we have introduced two theories. This is invariant under the global UN transformation. This with U constant UN matrix, i.e. the theory has the global UN symmetry. B is invariant under local UN transformation. This with UX any UN matrix. The theory has UN gauge symmetry. On the other hand, consider follow allowed operators in the two theories. In A, operators like these are allowed, although it is not invariant under global UN symmetry. But in B, allowed operators must be gauge invariant, so this is not allowed. So if we consider gauge series, Lagrangian, the allowed operators will be single trace operators, multi-trace operators. We denote single trace operators as OK. We project different operators. Then multiple trace ones will be like this. So general observables will be correlation functions of gauge invariant operators. Here we focus on local operators. Note that it is enough to focus on single trace operators since multiple trace ones are a product of them. Since we are working on in the Hooft limit, we want to know how correlation scales in the larger limit. There is a trick, consider this. Then the correlation in case 1 can be expressed as this. With OI single trace operators, SEFF has a form and trace this. So we have this, apply equation to this. All leading order contributions come from planar diagrams. Physical implications. The larger limit of 0 can be interpreted as creating a single particle state. Similarly, this will represent n particle state. Since this, we can diagonalize them such that this. There's no mixing between single trace and multiple trace operators in the larger limit. The first term means the multiple of independent propagators of O1 and O2 states. The second term scales like this. Note that it is not necessary there exists a stable on-shell particle associated with OIX0. The fluctuations of globules are suppressed. Suppose O is not O and the variance of O is this. Also, the first term scales as this, while the second term scales as O1. Just in the large n limit, it is more like a classical theory. So there is homomorphic between objects which have same number of holes. This proof is related with Hawking entropy, agent state correspondence theory, and hologram theory. So with the concept of infinity, we can solve every problem of ICM.